Welcome to the channel, guys. Today we're going to be doing something a little bit different and taking a look at some theory. In particular, we will be discussing two famous inequality theorems, the AMGM inequality and the Cauchy-Schwarz inequality. What we are starting with here is the AMGM inequality. What it says is that if I give you a list of positive numbers, x1, x2, all the way to xn, they're all positive, then their arithmetic mean, which is this quantity on the left-hand side, is greater than or equal to their geometric mean, which is this quantity on the right-hand side. And so this is actually a really useful theorem because it helps relate sums and products, which, as it will turn out, is really useful in a lot of places. And it's actually also really easy to remember because the arithmetic mean is just summing them all up and dividing by n. The geometric mean is multiplying them all and taking the nth root. So let's start by proving this theorem. And what we'll do is we'll first take a look at the case n equals 2. And what we get is that we want to show x1 plus x2 over 2 is greater than or equal to square root of x1, x2. And by the way, taking a look at some small cases is always a pretty good introductory method whenever you want to work with an expression like this. And what we can do is we can multiply both sides by 2, so we get x1 plus x2 is greater than or equal to 2 root x1, x2, and we can move this to the left-hand side to get x1 minus 2 root x1, x2 plus x2 is greater than or equal to 0. This is what we want to prove because all these steps are equivalent and reversible. And we can actually factor the left-hand side here into root x1 minus root x2 squared. If we were to check for yourself and expand this, it should be the exact same as that. And so we get that this is just equivalent to proving this inequality. But because all squares are non-negative, this inequality is obviously true. Hence, our original expression is true, and the case n equals 2 does indeed hold. And after we've proved the case for n equals 2, we now want to work on the general case for n. And what we can do is we will start by making a little bit of a simplification. What I mean by that is that we can assume that their geometric mean is 1. The reason is that these two expressions on the left-hand side and right-hand side, they're both homogeneous, which just means that they're to the same degree. For example, this is degree 1, this is degree n, but taken to the nth root, which means it's still degree 1. And for example, if let's say our geometric mean was, let's say it's r, so it's not 1. But then what we could do is we could just divide both sides by r, and then the geometric mean would obviously equal to 1. And then the left-hand side, so first of all, we're going to divide every term by r. So for example, x1 goes to x1 over r, and so on and so forth. And then on the left-hand side, we would get x1 over r plus x2 over r plus all the way to xn over r. And this is just the same as dividing the entire expression by r, so it would be equivalent. And this is what it means by a homogeneous expression. This expression is homogeneous, and so we can assume that the product is just 1. Okay. So we assume that x1, x2, all the way to xn, their geometric mean is equal to 1. And what we can do now is we're going to prove by induction, which means that we will assume that this theorem holds for the case n equals k. And then we want to prove that it also holds for the case n equals k plus 1. What we can do is, well, first of all, among the numbers x1, x2, all the way to xn, we know that they can't all be greater than or equal to 1. I mean, they can't all be greater than 1 because their product cannot be equal to 1. And we also know that they can't all be less than 1 because their product will be less than 1. Hence, we must be able to find a number that is less than or equal to 1 and another number that is greater than or equal to 1. So with that loss of generality, let's say that x1 is greater than or equal to 1 and x2 is less than or equal to 1. It is true that we must always be able to find these numbers. And so what we're going to do is that, for example, if we do x1 times x2, and then we also take a look at x1 plus x2, then there's a factorization that we can do to compare these two quantities. In particular, we have that x1, x2 minus x1 minus x2 plus 1. This thing can be factorized into x1 minus 1 times x2 minus 1. But then we also know that since x1 is greater than or equal to 1, this is greater than or equal to 0. x2 is less than or equal to 1, so this is less than or equal to 0, so the entire quantity is less than or equal to 0. Hence, we have that x1, x2 is less than or equal to x1 plus x2 minus 1. Okay, we will just keep that there, and we'll see how that will be useful for us later. And what we can do is that we want to prove that x1 plus x2 plus all the way to xn over n is greater than or equal to this nth root of x1, x2, dot dot dot, xn. But we assume that their product is 1, so this should just be 1. And essentially we just want to prove that the sum is greater than or equal to n. And we can actually rewrite this as x1 plus x2 is greater than or equal to x1, x2 plus 1. So now we can actually use this fact because you see, we have an x1, x2 plus x2 over here. And so this thing should be greater than or equal to, x1, x2 plus 1 plus dot 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 plus x3 plus, x1 plus x3 plus dot 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 plus all the way to xn. And what's neat is that if we take a look at this term, all these terms, we know that their product is equal to 1. Hence, their sum, by our induction hypotheses, has to be greater than or equal to n minus 1. And if we add 1 back, then this has to be greater than or equal to n. And so we have completed the inductive step, and so the AMGM inequality does indeed hold for all n. And so we have proved the AMGM inequality. What we're going to do next is we will be taking a look at a generalization of the AMGM inequality, which as follows. It is called the power mean inequality, or specifically the weighted power mean inequality. It looks a bit complex, but let me explain for a bit. So we're defining this, which is the power mean. We're defining this, the power mean expression, and what it essentially is that, for example, if I give you some numbers a1, a2, a3, all the way to an, what I define as the t power mean, so mt, we first take all of the numbers in our list, we take them to the tth power, and then we sum them all up, we divide it. That is a very ugly line. We divide it by n so that we get quote unquote the average, and then we take it to the 1 over t, which tth root, if you will, and that is our t power mean. So essentially, if you think about it, we're taking the t powers and then we divide it by n, so we get kind of like the average of all the t powers, and then we take it to the tth root again. So in some sense, this is a mean, and we define it as the tth power mean. Tth power mean. And, we also define this, and the reason for that is that, for example, if we put t equals 0, then we get 1 over 0 here, which you can't really divide by 0. So what we do is we explicitly define the 0th power mean to be equal to the geometric mean, which we have just taken a look at, which is nth root of a1, a2, all the way to an. And we also, this is the normal power mean, but we also add weights. to get the weighted power mean. And what the weights do is that, well, they're weights, so they skew the means on one side, to one side. So for example, for the 0th power mean, if I were to weight it, instead of giving everything an equal weight, I would write m0 is equal to a1 to the weight 1, so this is the first weight, times a2 to the weight 2, all the way to an to the weight n. And then we also make sure that the weights add up to n, so there's nothing weird. Sorry, add up to 1, so there's nothing weird happening. And for example, the normal geometric mean would just happen when all the weights are equal, when they're all equal to 1 over n. That would give us the normal geometric mean. And for the tth power mean, how we do the weighting is we just add the weights in front, we add the weights in front of this sum, and then we can also get rid of this. So this is the tth weighted power mean. Okay, so with all these definitions aside, what this theorem states is that if we have two quantities, r greater than s, then the rth power mean is greater than or equal to the sth power mean. And by the way, here we are fixing all the a's, and we're also fixing the weights, because otherwise it would get a bit messy and it would have been true. So we fix all of these, and then we take any r greater than s, then the rth power mean will be greater than or equal to the sth power mean. So specifically, when we plug in, for example, r equals 1 and s equals 0, then we get that the first power mean is greater than or equal to 0th power mean, which is the arithmetic mean is greater than or equal to geometric mean. That's just the AMGM inequality. And so the power mean inequality is a generalization of our AMGM inequality. And it's also very useful. For example, if I were to compare some quantities raised to a certain power, we know that the bigger the power is, the bigger the mean will be in general. Okay, so that is the weighted power mean inequality. We will not go over the proof in this video because it is quite complex, but it is a very useful inequality that we should always learn. Okay, and then now we will be moving on to the next inequality, which is the Cauchy-Schwarz inequality, as I previously mentioned. And with the Cauchy-Schwarz inequality, I'm giving you two lists of numbers, a1 all the way to an, that's list number 1, and then b1 all the way to bn, that's list number 2. And unlike AMGM, these numbers can be negative. In AMGM, they can't really be negative because, for example, if I just had x1 is negative and everything else is positive, then we'd be taking a negative square root, and we can't do that. We're dealing with real numbers. So with Cauchy-Schwarz, there's actually not that problem. And the Cauchy-Schwarz inequality states that if I were to square each of these terms, take their sum, square each of these terms, take their sum, and then I multiply the sums, which is just the left-hand side, that would be greater than or equal to this quantity, which is if I were to, for example, multiply these together, multiply these together, add them all up, and take the square. Okay, and this is actually also quite a useful inequality in solving problems. Arguably, it's more useful than AMGM, but it's up to debate. But they're both really useful, and essentially, for example, with Cauchy-Schwarz, you can do a lot of clearing denominators and radicals. So for example, if I were to have, let's not confuse ourselves with the notation. Let's say if I were to have something like an expression like this, then I can use the AMGM, or rather the Cauchy-Schwarz inequality. For example, if I were to multiply by y1 plus y2 plus y3, we can do the Cauchy-Schwarz to multiply these two together, so we get x1 square root of x1 plus square root of x2 plus square root of x3, square root of x3. This is greater than or equal to this thing squared by the Cauchy-Schwarz inequality. We won't go through much of the applications, but I just want to make a point that the Cauchy-Schwarz inequality is indeed very useful. And we will now actually prove the inequality. how we'll do so is that we'll define a function first. The function is, let's say in x, then we have f of x is equal to a1x minus b1 squared plus a2x minus b2 squared plus all the way to anx minus bn squared. And by the way, I just want to take a quick note that in AMGM, the equality holds. You see there is an equality sign, which means that it does sometimes hold. The equality holds when all the quantities are equal, if and only if all the quantities are equal, which means that x1 is equal to x2 is equal to all the way to xn. They're all equal, and you can see for yourself why it would hold. And similarly, in the power mean inequality, the equality holds when all our lists, the a1 to an, they're equal. By lists, I mean the a1 to an quantities. If they're all equal, then the power mean will be equal for different r's and s's. But obviously there's probably some special cases, like for example, weight 1 is equal to 0 and everything else, weight 1 is equal to 1 and everything else is 0. But those are quite trivial cases, and we usually don't deal with them. With the Cauchy-Schwarz inequality, equality holds when the ratio between the lists are the same. So these two ratios are the same, and by convention, for example, if this was 0, then this must also be 0 for the ratio to be the same. Okay, so going back to the proof of the Cauchy-Schwarz inequality, if we define a function like this, we can expand this out first of all. So for example, if we take a look at the x squared term, this would be a1 squared plus a2 squared plus all the way to an squared. That's looking a bit like that. That's quite suspicious. Okay, let's move on. And for the x term, for example, if we take the x term from here, it would be negative 2a1b1, so 2a1b1. And then similarly, the other ones will be 2a2b2 all the way to 2anbn. And finally, for the constant term, that would just be the squared. So b1 squared plus all the way to bn squared. And that's looking like this. And since it's a sum of squares, f of x is a sum of squares, f of x is always greater than or equal to 0. And we can also write f of x as a quadratic in x. And what that tells us is that whenever a quadratic is always greater than or equal to 0, its discriminant must be less than 0 or less than or equal to 0, and its leading coefficient must be greater than or equal to 0 or greater than 0 in this case. And that's true here since the quantities are all squared, and we're not making a1 to an all 0 because that would just be trivial. Anyways, we want the discriminant to be less than or equal to 0, or we know the discriminant must be less than or equal to 0. And the discriminant is the leading coefficient squared, the second coefficient, which is the thing over here, squared, and we can take out the common factor 2, so we get 4 a1b1 plus a2b2 plus dot 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 plus anbn. This thing squared minus 4ac, which is 4 times this, so 4 times our two list sums. And we know that this will eventually be less than or equal to 0. So if we rearrange this, for example, we cancel out the 4's and we rearrange this, then we get that a1 squared plus a2 squared plus dot 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 plus an squared. This thing will be greater than or equal to, multiplied by b1 squared plus all the way to bn squared. This thing will be greater than or equal to this thing right here, which is a1b1 plus all the way to anbn, and then I take the square of the entire expression. Yeah, and if we notice, this is the exact same as what the Cauchy-Schwarz inequality tells us. And I personally really like this proof, And if we were to check the equality cases, it will only hold when all of these terms must be equal to 0, which means that their ratios are all the same. And so we have proven the Cauchy-Schwarz inequality. And what we'll do for the last part is we will take a look at a generalization of the Cauchy-Schwarz inequality, which is Holder's inequality. And this looks a bit more complex, but it's essentially the Cauchy-Schwarz inequality generalized to not just two products, but n products. And also we're adding weights. So for example, if I were to give you a list of numbers, and a list of numbers, let's say we start from A11, A12, all the way to A1n. This is our first list. And then let me give you a second list, A21, A22, all the way to A2n. And then I were to give you n lists, m lists in total, all the way to amn. And then, similar to the Cauchy-Schwarz inequality, if I were to sum all these up, sum them all up, which are these things right here, and then I take them to the power of their respective weights. And by the way, here, again, we are assuming that the weights sum up to 1. I take them to the power of their weights, then that quantity will be greater than or equal to if I were to take this thing, take it to the power of its weight, multiply by this thing, taken to the power of its weight, all the way over here. I take this product and I add it down to whatever the product down here is, and then I keep adding it down to this last one. That quantity will be smaller than our first quantity, and that would result in something looking like this. So this is actually quite useful also as a generalization of the Cauchy-Schwarz inequality. We will not go over the proof, but I just want to quickly talk about a few applications. So for example, you could treat this as a weighted Cauchy-Schwarz if you don't want to use all of the multiple lists. For example, if I just had our normal, A1 plus A2 should be, we can treat this as a weighted Cauchy-Schwarz because if I take this to a certain weight, and then I multiply this by our B1 plus B2, all the way to Bn taken to another weight, this is greater than or equal to if I were to sum A1, W1, B1, W2, plus all the way to An, W1, Bn, W2. And the normal Cauchy-Schwarz inequality arises when W1 is equal to 1/2 and W2 is also equal to 1/2. Finally, we can also do 3 variables, which is, or rather, 3 of these product things. I won't write too many terms just to keep it clean, but for example, if I were to do this, this has to be greater than or equal to A1, B1, C1 plus A2, B2, C2 cubed. Because, for example, these should be cube rooted right here. Cubed. And this is just an application of Holder's inequality by taking these to the 1/3, and then you sum these all up, take the product and you get this, take the second product, you get this, and then you cube it because you wanted to take this to the first power. Yeah, so in this video, quick summary, we talked about the AMGM inequality, we proved it, but essentially it's really useful for relating products and sums. And then we talked about a generalization of the AMGM inequality, which is the power mean or the weighted power mean inequality. And this not only relates to products and sums, it also relates to sums of higher powers, which can be really useful sometimes. Then we have the Cauchy-Schwarz inequality, which is good for talking about lists of numbers. And one thing I like to think about is that with the Cauchy-Schwarz inequality, we sort of have a product being greater than or equal to something else. So for example, if we normally had a product, then with AMGM inequality, the GM, then this is usually less than something. But with Cauchy-Schwarz, you can make it a bit bigger than some other stuff. So That's helpful a lot of times, and the Cauchy-Schwarz inequality is definitely really good for clearing denominators, clearing radicals, and all that stuff. And then finally, the Holder's inequality, which is a generalization of Cauchy-Schwarz inequality, can help generalize it to more lists and also use weighting for when the problem seems to request an application of that sort.